Hi folks, we are on the very last lesson of our Unit 1 work. This is Unit 1, Day 9. We're going to talk about linear combinations of vectors and what a spanning set is. So this is a little bit more theoretical, and this is kind of leading into what we're going to be doing more of in Unit 3, but we just kind of dip a little bit of our toe into this and start looking at the idea behind vectors forming a plane and forming kind of objects in 3 dimensions that we're going to be able to examine more deeply when we get to the lines and planes unit in Unit 3. So the first thing we're going to talk about here is collinear vectors. Remember that collinear vectors really just means 2 vectors that are parallel, and they can be written as scalar multiples of each other. So we've talked about collinear vectors more in terms of geometric vectors, but what would that look like with algebraic? So in this example, we have 4 points, and we want to know are vectors A, B, and C, D collinear. Now remember, to find a vector from one point to the other, we're going to subtract the x values, subtract the y values, and subtract the z values, and the order does matter. You're doing the end point minus the starting point. So here for the x's, I have -1 minus 2 is -3. Careful with double negatives. You don't want to make a careless error in here. 2 minus -3 is 5. -2 minus 5 is -7. And then we'll do the same for vector CD. We'll find out what vector CD is equal to by subtracting. So we start at C, end at D. You take the end point minus the starting point. 4 minus -5 is 9. -6 minus 9 is -15. 15 minus -6, so plus 6, is 21. So if we take a look at these vectors, remember that when we learned collinear vectors, we said that 2 vectors were collinear if and only if they could be written as a scalar multiple of each other. So if we can prove that these vectors are scalar multiples of each other, then we know in fact that A, B, and C, D are collinear. And you probably notice, hopefully notice, that yes, if we look at the x values, -3 times -3 is 9. 5 times -3 for the y values is -15. -7 times -3 is +21. So we see multiply by -3 and we get to that. So that is really, we're just going to be doing these by inspection. So we could say yes, since, and the symbol for since in math is an upside down triangle of dots, kind of the opposite of a therefore. So since CD, vector CD, equals -3 times AB, you could write that the other way and say that the AB was -1/3 times CD. Therefore, vector AB is parallel to or collinear with vector CD. So we just kind of recognize this relationship, and it has to hold through, obviously has to be true for all x, y, and z. Has to work for every piece of those vectors. So here, this is a little bit of a different story. We're given 3 points, and we want to know if those points are collinear. Now, I'm going to draw them out, and obviously like not real accurately or anything, but just to kind of say I've got A, B, and C. Maybe they're collinear, maybe they're not. It's a little bit crooked there probably. So there's different ways to approach this, but basically we want to find 2 vectors using these 3 points. And this is going to be really similar to, I feel like you guys do this, and I actually do this with my grade 9s when they're doing slope. And we kind of look at it and say, oh, is the slope from A to B the same as the slope from B to C? And that's sort of what we're going to do. So I'm going to draw in two different vectors here. I'm going to draw vector AB, and then I'm going to also draw, get myself a different color, vector BC. Now you could easily do this with, say, vector AC and AB. It doesn't actually really matter. You have to include all 3 points in your slope calculations though. So now I'm going to find vector AB. So again, subtracting 2 minus -3 is 5, -1 minus 5 is -6, and 4 minus 1 is 3. And then I'm going to find my second vector, BC. And again, you could have used AC. We could have used AC and BC, any combination here. And just check if they are scalar multiples. So BC, I'm doing the C points minus the B. So -8 minus 2 is -10. 11 minus -1. So that's +1 is +12. And here you may be starting to look and say, oh, look, that's times -2, that's times -2. We maybe are on the right track for these to be collinear. But here I've got -1 minus 4. So that's -5. So these are not going to be, because if we tried to multiply the x's by -2, yep, that works. The y's times -2, that works. But the z's, 3 times -2 is -6, not -5. So we don't have collinear points here. These points are not all in a line. One of them is just a little smidge off. So we would say no, they are not collinear, because, and I'm going to just kind of say mathematically that AB, vector AB is not equal to k times vector BC for any real number k. I cannot find a scalar multiple of one that would make the other one equal to it. So those three are not collinear.